Hey guys, we're going to take a look at your first flipped lesson. Today we're going to be looking at the same thing that we looked at in class last time, but now we're going to be looking at it in a more formal way. Last time in class we took a look at this example from Mr. Harrison's gym, Mayfair CrossFit. He charges $90 a month for a full membership and $75 a month for a discounted membership. In the gym, there's only enough room in class times for a total of 50 members. How many people does he need at each type of membership to make $4,050 per month? So I had you in class do a little bit of exploration with this and talk with your friends a little bit and try to figure it out yourself. And what we came to the conclusion was that we were missing two things, two variables, but we also had two requirements. So what this led us to was two separate equations. One equation here, the top one, deals with the amount of money per membership for a full member and the amount of money per membership for a discounted member. And then we wanted that to be a total of $4,050. Then we had the amount of members at the full membership and the amount of members at the $75 discounted membership. And we wanted the total number of members to be 50. So that was two separate requirements. In the real world, when you have multiple requirements like this, you have to make sure that you're meeting all of the requirements. This leads us in math to a concept called a system of equations. If you look at your notes that I gave you in class, there's three systems of equations at the top. You can try to graph these before I do this in the video. We're going to come back to those in just a minute. I'm actually going to kind of skip ahead here. I'm going to skip down to number 4 on your little guided notes that I gave you. Number 4 actually defines what a linear system is. A system of equations is a group of equations with the same variables. You'll notice that both of those equations that we looked at for Mr. Harrison's gym dealt with the number of full memberships and the number of discounted memberships, or specifically the members. So those are representing numbers of people. Each equation, though, was talking about a different side of those memberships. One was talking about the money that it brings in, and the other one was just talking about simply how many people show up. Yes, Mr. Harrison realizes that it's okay to have more than that $4,050. I also realize that it's okay to have more than 50 members or less than 50 and make more. What we were looking at here is trying to meet both requirements exactly, and then we're going to expand a little bit further into times when maybe we don't meet both requirements exactly. So a system of equations is a group of equations with the same variables. For you guys, typically that means the number of variables is going to tell you how many equations you need. Or in other words, the number of variables is going to typically be equal to the number of equations. Now, that is not always going to be the case. As you learn more ways to solve these, as you get into higher levels of math, you may work with times when that's not the case. For the most part, though, you can bet that most of your high school mathematics and maybe even some of your early college mathematics will involve you looking at times where you have the same number of variables and the same number of equations. In other words, 2 variables, 2 equations, 3 variables, 3 equations, 4 variables, 4 equations. We're not going to get quite that high, though, in this class. So when you look at number 5 on your little guided note sheet, I'm not going to write those on the screen here. If you look at number 5, A would be a system of equations because it involves 2 equations with x and y. B would not be a system of equations because it has 2 equations, but they have different variables. Like I said, unless you get into some higher levels of mathematics, you can't deal with that. C is a system of equations because it involves 2 equations with A and B. And D That one's a little tricky when you first look at it. It actually is a system of equations because it involves two equations with x and y. Hold up, Mr. Harrison, you're a liar. That second equation doesn't have a y. It actually is just like writing x plus 0y equals 2. Or in other words, just look at the equation. There's no new variables in that second equation. So what that's telling you is, really, it's a really easy one. X is 2. It's actually telling you part of the answer anyways. Because what we do with these, if you look back on the screen now and focus in on it a little bit closer where I'm at, you can use all of the equations to find the solutions for all of the variables. So what is a solution to a system of equations? Well, if you look at number 6, the solution of a system is the numbers that satisfy all of the equations. I'm going to highlight that word all here because that's the key. The key requirement for Mr. Harrison's gym that we looked at in class was that he wanted it to make $4,050 per month, but he also wanted 50 total members. I know that some of you said, well, I can make more than that for you. That's not what I'm looking for at the moment. We'll talk about some more real-life consequences of this particular problem in class next time. The key is I was trying to meet both requirements exactly. And that's what a solution to a system does. A solution to a system satisfies all of the equations. We will also look at some inequalities before the end of this video. For two variables, that means we're going to be looking for an ordered pair, an x and a y value that gives me the solution to the equations. I was looking for the number of full memberships and the number of discounted memberships. So this is a little different than what we did in the first chapter, where we were trying to find a solution that works for an equation. We may have just been working with one equation, and so we could have had infinite solutions. Or even near the end of the chapter, when we used Desmos to go through and actually type in an equation and then find the solution by finding out where that equation intersects with another equation, we were just looking at then one particular point. One particular point, though, also has two values to it. At the end of last chapter, we were looking at just finding the x that solves an equation, because that's all we were looking at is two equations set equal to y. Sorry about the bell interrupting there. Let me take a pause while they announce people leaving class. Hold on just a second. So I have to apologize. I had to take a little break there because I also forgot I had car duty on Friday afternoon. So let's finish out this video here. Let's talk about finding the solutions to a system of equations. So as I was saying, a system of equations is a group of equations in the same variables. You can use all of the equations to find the solutions for all of the variables. But a key word there, again, is all. The solution has to work for all of the equations. When we look at that example with my gym, Mayfair CrossFit, no, I'm not advertising, I promise. Just kidding, maybe. So anyways, when we look at the $90 membership, $75 membership, and want to make $4,050, but also want to get 50 people. When we look at that graph of each one of those equations, it's not just the x value that means something to us, like we looked at in the last portion of the last chapter. It is also the x and the y. So notice when we find the point where these two intersect each other at 20 and 30, that means more than just the x value. The x value and the y value mean something for us. It means I want 20 people at $90 a month, and I want 30 people at $75 a month to meet both of these requirements. And so what we are talking about in this first section of this chapter, this new chapter, is solving these systems of equations by graphing. We are looking at graphing two equations with two variables and seeing where they both touch. Because if you'll remember back to the very first chapter that we did, the solutions to any equation are the points on the graph that work for that equation. Remember, that was the whole reason for graphing a line in the first place. So when we graph these linear equations, we are finding the solution that works for that whole equation. When we graph two of them, we see if there's a solution that works for all, or specifically both of the equations when you deal with two variables. So there are three different types of answers that you can get. So let's take a look at number one at the top. So I'm kind of going back up to the top now, and we're going to fill in the chart at the bottom of the page also. So y equals 2. If you remember, that is a horizontal line. Again, pause this if you want to try these before I graph them to see if you get them right. Y equals 2 is a horizontal line across the graph at y equals 2. Because that is what it's telling me. It's telling me the y value is 2 the whole time. Every point on that line has a y value of 2. Y equals 3x minus 1. Remember the good old y equals mx plus b stuff, where you begin at a point and move to the next value. Notice you would begin at -1 and then move up 3 over 1. Up 3 over 1. That is graphing a linear equation. Again, every single point on that line, the whole point of graphing, yes, pun intended, the whole point of graphing is that every single one of these points on this line are solutions to that equation. But when we talk about a system of equations, we are trying to find what point would work for both equations, just like we talked about with my gym. So which point on here would work for both equations? That's right, I hear you yelling it. It's 1, 2. That point, 1, 2, would be the solution to this system. Not only is it a solution to this line, but it's also a solution to this line. It is the solution to both equations. That's the point of this process also, is that point 1, 2, if you plug in 1 for x, 2 for y, it works in this equation. 1 for x, there ain't no x. 2 for y, it equals 2. So this point is the only solution that works for both equations. Just like what we looked at with this guy over here, when we have those two equations and they're a little bit uglier, a little bit bigger numbers. But do you see with these bigger numbers, if we don't have technology to help us graph it, we want to stick to smaller numbers if we're going to graph typically. When we get into some larger numbers, and even graphing is not pretty on a computer, I'm going to show you an algebraic way to solve these as well. That way, if you don't have access to a graphical method, whether that be through technology or by hand, you can still solve these. So the first type that you should put at the bottom of the page down here in that little table that you see at the very bottom, the first type that we see at the top up here is if you have two lines and they intersect each other, or in other words, they are intersecting lines. And yes, I know I'm putting this in the box here because that is not the name of this system. It's just the types of lines. When you have intersecting lines, they will touch at one point because they're linear. Notice we also looked at some that had lines and curves in that first chapter. We'll come back to those a little bit later in this chapter. But that gives you an x value and a y value that is a point on the graph. So that point where these two guys touch each other is the solution. So that means there's only one solution. Now that's not what I want you to answer. I want you to actually answer x and y from the point. So please don't get confused here. Make sure you understand that's the actual answer to the problem. Yes, there's only one answer. It's a point, but it does have an X and a Y value, just like we had 20 members and 30 members for Mr. Harrison's gym. The name of this one and the name of all three of these is kind of weird. It's called consistent and independent. I'm going to ask you these names maybe as like a little bonus in the quiz, maybe a small portion of the final test. This is not the most important part. The names of these are not the most important part. The only reason we teach you the names of these is so you can keep them separate as three separate possibilities, because even when we don't use the graphing method, you still have the same three possibilities. So this one is called consistent and independent. Consistent means it has an answer. Independent means there's only one point where they touch, or one answer. Obviously, this changes when you get into some things that have some curves. Number 2 at the top. On this one, I do have to subtract 2x first from both sides on the first equation, because that will cancel out and leave me with y equals 3 minus 2x. Meaning I begin at 3, then I move down 2 over 1, down 2 over 1. Yes, I know. That whole begin and move gets on your nerves, and I don't care. So we have this as our line. Now, when you go to the other one, it is already solved for y. So you begin at -1, and then you move down 2 and over 1, down 2 and over 1. What do you notice? Oh, yeah. I heard you say it. I did hear you say it, I think. Just kidding, guys. All right, so, oh my goodness, this line's giving me issues. Here we go. Notice that this line is parallel to the first one. What does that mean, Mr. Harrison? They don't touch each other. You're right. So think about it. Would there be a solution that works for all of the equations? Now, don't get me wrong. If you look at the blue line here, every point on this blue line is a solution to this equation right here. Every point on the red line is a solution to this equation right here. Don't misunderstand me. We still have solutions for each individual equation, like we did in the first chapter. What's different now is there is no solution that works for both equations. Because guess what? If they don't touch each other, that means there's not a solution that works for both equations. So take a look at the bottom of your page again. Down to our little table here. Notice when you have parallel lines, I'm going to write that word in this little box as well. Parallel lines do not touch each other. That means there is no solution. Yes, technically that means none. I would rather you write no solution, just that way you have enough detail there to make sure people understand what you are telling them the answer is for that system of equations. This one would be named inconsistent. Inconsistent. Think about it. The word consistent in the first one means it had an answer. Independent means there was only one. So if consistent means it has an answer, inconsistent would mean it doesn't have an answer. And I don't have to put any extra words with that one. So there's only one more type. Some of you might be able to guess what it is, but this one requires you to do a little bit more work because they're not solved for y. Again, pause the video here if you want to try them before I do it. The other type is, if I subtract x here, that gives me -2y equals 4 minus x. I divide by -2. When I divide by -2, 4 divided by negative 2 is negative 2. Negative 1 divided by negative 2 is positive 1/2. That means I would begin at negative 2. Remember, mx plus b, the m is always beside the x. And then I would move up 1 over 2, up 1 over 2, up 1 over 2. This is a beautiful line here, right? Yeah. What we get here is we get a bunch of solutions again. Remember, the whole point of graphing is that every single one of these points is a solution. I could start listing out some solutions like 0, negative 2 right there. 2, negative 1 would also be a solution. I could keep on going if I wanted to. All of those are solutions to this equation, to this line. Then I look at the other one. If I add 2x first, get it to the other side. When I add 2x, that gives me 4y equals negative 8 plus 2x. I divide by 4 on both sides. That gives me y equals negative 8 divided by 4 is negative 2. 2 divided by 4 is 1/2. Oh. Now some of you are going, Mr. Harrison, I still don't get it. What are you getting at? Notice it goes and begins at negative 2 and moves up 1 over 2. Holy cow, it's the same line, Mr. Harrison. Yeah, I know. It's awesome, isn't it? Isn't math great? Yeah, I know some of you are laughing at me. I get it. It's okay. So if you look, the same points, 0, negative 2, 2, negative 1, and we could keep on going forever if we wanted to, are solutions to this equation. In other words, every single point on this line, even some of the decimal points in between. Please don't forget that. I know I've been kind of focusing in on the fact that we're looking at these easy points here, but even some of these little fraction points in between, like right there, that's still a solution because it's on the line. And because this particular example, both lines end up being the same line, that means every single point on the line is a solution to both equations. One way I've seen people talk about this is talking about calling them the same line. I've also just seen people use the word overlapping. Not personally my favorite line, but the same line. How many solutions would that be? Hopefully you're screaming at your TV screen because you're watching this on your YouTube app. Just kidding. Or you're going through... I'm sorry, guys. Terrible jokes. I'm just trying to keep myself entertained while I teach you. Infinite solutions is hopefully what you're screaming there, because every single point on the line is a solution. That means it has a bunch of answers, not just one answer like the first one did, because they only intersected at one point. Not no solution like the second example here where we had parallel lines, but it's the same exact line. So every single point, every point on the line works. Please don't forget that. I'll make a little side note of that down here. It's every point on the line, because that right there, every single point would work for both equations. We call that infinite solutions. And I'm okay with you answering it as no solution when it's parallel, and infinite solutions when it is the same line. That's okay with me. Just like I had the point when it was one solution. So, we'll talk about sometimes you will want to actually get some of these points, but not every time. Now, guys, this is just for linear systems. When you get to things that are not linear, yes, you can have more than that. So what would the name of this type of system be? Consistent. Wait a minute, Mr. Harrison, you already used that one. I know. Remember, consistent means it has an answer. Independent means it was only one. This one is actually dependent. Consistent and dependent. So what I like to tell people, and it's kind of a goofy way to remember it, so don't laugh too hard at me, But you all know that real dependent boyfriend or girlfriend. Sometimes we give them the affectionate name of a puppy dog boyfriend or girlfriend, the one that follows the other one around the school everywhere. I don't think we have anybody in our class like that. Cough, cough. But there are some probably that you know who follow their boyfriend around everywhere or follow their girlfriend around everywhere. We know those people who are dependent upon the other person. But notice what we just said. They're always with each other. That's how I try to tell people to remember this: consistent and dependent. Think about that dependent boyfriend or girlfriend who always follows their significant other around everywhere, right? So, they got to walk each other to class, right? These are the 3 types of answers that you will get with all of these linear systems and 2 variables. Yes, we are going to expand on this a little bit, and we're going to look at inequalities as well. We're going to expand on this a little bit and look at more than just 2 variables, and it changes things up a little bit. But you still have these 3 types of answers for the 3 variables. The problem it starts to get into when we run into some that are not linear. Remember, we had some in the last chapter where we had a curve and we had a line. I'll give you an example of that real quick. Think about those little parabola shapes that we talked about, and then having a line. If you wanted to find the system's solution, the solution to this system here, you would have to know where this point is and this point is. Notice there's not just one answer like we have with 2 lines. So it gets a little different when you get into things that are curved. But we'll talk about those as we go through in the later parts of the chapter. And 3 variables and inequalities, we're going to take a look at those real quick, just because they tie directly back to these a little better, with linear inequalities being graphed basically the same way that linear equations are. So this will be the last thing we look at in this video, is what happens when you have 2 linear inequalities, not just linear equations like we looked at over here. Now, on the back side of the sheet that you have for notes, you'll see there are some practice problems that you can play around with, but we are going to do some in class. Remember, that's the whole point of a flipped lesson. So when you look at those on the back, if you want to try some, you can. I'm not going to make you. They look very similar to these, and you're solving them by graphing. I want to finish out, like I said, with looking at linear inequalities. Remember, the difference with inequalities is that you have that shaded area. So you're going to graph each inequality and shade it just like we did in the first chapter. And then you're going to have an area that's shaded by all the graphs. So instead of just one solution, one point, you may have a solution region that we call that. So that is going to look like something like this guy. Y is greater than or equal to negative 3x minus 1. Think about what we did in the first chapter with these. We took a look at negative 3x minus 1 and realized, hey, that's that mx plus b stuff again, Mr. Harrison. Yes, so you begin at negative 1. Then you move down 3 over 1. Down 3 over 1. Here's the difference. Now when I graph this, because it has an equal to sign underneath it right there, I have to graph what we called a solid line. And then I also had to shade this graph greater than that line. Now remember what I said. I gave you a little clue in class. I said take it, put your finger on the line, and shade above the line. This would be all the solutions for that inequality. This would be all the solutions. The problem is, we want to know where all the solutions are for the whole system of inequalities, not just one inequality. So basically, this is kind of like what some of you maybe wanted to do with Mr. Harrison's gym when you wanted him to make more than $4,050. That would be a greater than problem. Or have less than 50 people. That would be also an inequality. So you look at this and you graph it basically the same way, and then you'll find an area that's the solutions. Let me finish this one out so show you what I'm talking about here. Notice this one is plus 2, so I begin at 2. My slope is positive 1, so I go up 1 over 1, up 1 over 1, up 1 over 1. But this one is going to be what we call a dashed or dotted line. And yes, this thing will do some weird things with the dots on the little shade areas, so don't panic on me. Connect my dots with a dotted line. And then I shade less than the line. So that would be everything below the line. Now look at your graph here and decide where would be the solutions for both inequalities. Notice it's a little different than equations. We're not just looking at this point here because actually this dotted line tells me no points on this line actually work. So the points on the blue line do work because they are solid, equal to, and they're in the little red shaded area. The points in the blue area and the red area that overlap work, but the points on the dashed line do not work. So in other words, your solution region is this little area over here that's actually shaded by both graphs. Now I'm not going to get real, strict about, oh, you better label your solution region. I'm not going to be that way, but it is helpful if Mr. Harrison's grading your test or a quiz or anything like that for me to tell where your solutions are. But if you need to, just shade it darker and let me know that way, that's fine. Just make sure it's obvious. Don't try to be sneaky, okay? So this area is shaded by both graphs, not just one. So let me do another one. I'm going to go over to this little guy here because this has a little trick to it. You can try it first if you would like. Okay, so let's look at the first little trick here. X is greater than or equal to 0. Mr. Harrison, that only has an X in it. Remember, Y is only a horizontal line. X only is a vertical line. And because it's 0, it's actually the vertical line that makes up the Y-axis. Now, I know that's kind of weird. That's why some of you struggle with vertical and horizontal lines. But a vertical line that's equal to 0, that's where X is 0. Where would greater than 0 be for X? Everything this way. This is the only time you think about shading to the right. Think about the old number lines that we used to do. But you'll have a solid line or a dotted line. Y is greater than or equal to 0 is going to be a horizontal line at 0. Again, notice this one is actually the x-axis, but remember, on the x-axis, the y value is actually 0. So this one would be a y value equal to 0. Greater than 0 for y would be above. Let me fix that. Y is greater than would actually be above the axis. So let me ask you, think about it. Don't blurt it out because I don't want anybody to hear you telling them the answer. Oh, wait. Can't hear you, can you? Where are the answers right now? The answers right now, hopefully you're screaming at your screen here, are over here in the first quadrant because that's where x's are greater than 0 and y's are greater than 0. The equal to would actually be the lines themselves. But Mr. Harrison, there's one more. You're right. So let's take a look at it. 4x plus 3y is less than or equal to 24. Let me use the orange. It's a little bit easier to see. If I subtract 4x like we did with the linear equations, I end up with 24 minus 4x. Yes, you do have to watch out here when you divide with an inequality. But since I'm dividing by a positive 3, I'm okay. I don't have to do anything weird there. 24 divided by 3 is 8. Negative 4 divided by 3 is negative 4/3 x. So you begin at 8. And then you go down 4 over 3. Down 4 over 3. Notice this one is going to be a solid line just like the other one. Oh boy, this thing's not going to let me. Oh, there we go. Sorry, guys. Again, does some weird things with the shaded area for some reason. has to do with how long it took me to do my shading. So I know it's kind of weird looking. So where do we shade this one? We shade it below that line. So it'll be everything below this line. Now you may be looking at that and going, well, crap, Mr. Harrison, that's the whole graph. Where's the answers? Think about where our original solutions were. Remember, we had this vertical line, and then we shaded everything that way. We had this horizontal line, and we shaded everything this way. Then we had this slanted line. Wow, I was doing okay until that point. It's okay. Slanted line and shaded this way. That means, yes, this little triangle is actually where the solution region is. So that means if you want to find the solutions that work for all of these inequalities, keyword all of the inequalities, you have to find the solutions that work for all of them by shading. It's not quite as simple as the equations where you just look where they touch, or if they don't touch, or if they're the same line. You only have 3 quick little possibilities. With inequalities, it is a little tougher, but the graphing is basically the same idea that we've looked at since that first chapter. So this is what linear systems look like for equations and inequalities. In the next part of the chapter, we're going to look at solving them with methods other than graphing. Because I know everybody's favorite thing is graphing, right? All right, guys, well, that's it. That's your lesson for Monday. We're going to take a look at this Monday and a little bit on Tuesday as well with a little bit of assessment to see how you do. Have a great weekend.